All right, well, good morning, everybody. And to those of you here live and those listening after in the recording, we're welcoming Thomas Brisky today from Aber Instruments. Thomas is a service engineer with Aber, and they make these capacitance measurement tools and other tools for all kinds of industries, including the food, brewery, and biotech industry. And today we're going to learn about capacitance and its applications to biotech. So very excited, Thomas, to have you here today, especially someone who does the on-the-ground work with industry, because that's what we're all about. So looking forward to hearing about those industry applications. Welcome.
Yep, thank you. So I'm here to present to you the Aber technology. As Doug mentioned, I'm Thomas Brisky. I'm a technical service engineer for Aber Instruments. My background is engineering and health sciences, but I lucked into getting into this field, which is a great field to be in. It's a pleasure to be here, and so today I'll discuss how Aber uses capacitance to measure viable cell volume and density across various applications. So basically in this presentation, we will try to answer a few of the basic questions, such as who are we as a company, why there is a need for the technology like Aber to be present in industry, and as importantly, how does the technology work? In other words, what are the principles of the Aber measurement? And finally, of course, we'll go through the technology, where it can be used, and where it has been used successfully over the years. So to start us off with our basic question, that being, who are we? Aber Instruments is situated in Midwest Wales in the town of Aberystwyth, which is being pointed at the map here. This is where the company was actually founded in 1988 and is where our headquarters is still today. Though we do have a subsidiary in the US where I'm from, specifically in the Washington, DC area, just because that is one of our larger markets and we want to have a local presence for especially service engineering. The interesting thing about us is Aber Instruments is actually the inventor of the technology, namely dielectric spectroscopy. We are the industry experts with over 30 years of experience in the field. In fact, one of the inventors of the technology still works for our company. And the good thing about our technology is it has successfully done the transition between research and development from colleges and universities to process development fields and all the way to manufacturing processes, which is quite important for any technology to be able to do. And we've been doing this transition over the past 15, 20 years. And now, and because of our wide range of offerings, our instruments are now used in all of those different styles. So anything from your mini and small glass bioreactors to your large stainless steel vessels. So now I'll move on to the next part question is, why is there a need for the real-time Aber technology? This is a good time to point this is a good point to discuss what process analytical technology, or PAT, is. The FDA's definition of PAT is a mechanism to design, analyze, and control manufacturing processes through the measurement of critical process parameters, or CPPs, which affect critical quality attributes, or CQAs. Everyone agrees that in the biopharmaceutical processes, one of the most critical process parameters is biomass, and knowledge of biomass is invaluable, especially in real time. Now, this is because the biomass will often have a direct impact on your product quality, your product yield, just basically everything you're trying to do with the bioreactor. The method to measure biomass should ideally be reliable, easy to use, real-time, and in situ. And dielectric spectroscopy satisfies all of those requirements and has been used to determine the live cell concentration in bioprocesses in real time successfully over the past 2 decades. Now, the challenges of offline measurements are well known and understood within the industry. Even with frequent sampling regimens, you end up with insufficient sample points and you miss critical events in the process. The sampling procedure exposes the bioreactor to risk. The offline sampling procedure is labor intensive, requiring a significant amount of investment in time and energy. But even after that investment of time and energy, the offline sampling procedure themselves are known to be innately error prone, and the error can be contributed to by the sampling procedure itself, the sample not being good representation of the entire vessel, the dilution process, as well as several other factors. The Aber technology, on the other hand, is real-time and has demonstrated to be accurate and consistent. There's no need for offline sampling, therefore all the challenges I discussed in the previous slide are eliminated. You can use the technology in both conventional and single-use bioreactors. And finally, because it provides a complete and real-time knowledge of the critical process parameter, that being biomass, not only can it be used to monitor, but also control critical process aspects. So that's another question answered. So we'll move on to the principles of the Aber technology. In other words, how does it work? Aber technology measures two basic parameters. We measure capacitance and we measure conductivity. And put simply, capacitance is the ability of any substance to hold a separation of charge around itself, whereas conversely, conductivity is the ability of any substance to give away charge. But why are these parameters important to us? To understand this, we need to go back to the basic structure of the cell membrane. The cell membrane, specifically for live cells, is quite unique because it doesn't allow the free flow of ions across its surface. Therefore, as shown in this graph, under the influence of an infinitesimal electric field, which the Aber generates, there's a buildup of charge across the live cell membranes. Therefore, every cell acts like a tiny capacitor because it has that separation of charge, as you can see in the graph, where those negative and positive ions are getting close to each other, but they can't touch due to the bilayer membrane. And so each one of those creates a capacitor, and the more you have, the more capacitance you have within your system. So this is just a simple demonstration of the same thing I was talking about earlier. What we have here is a live cell representing yellow. The blue circle is the bilayer membrane, and we have a positive electrode on the left, negative electrode on the right. And then we have ions inside the cell cytoplasm, and we have ions on outside the cell as well. When there is no electric field, all of them scatter around haphazard. As soon as you induce electric field, represented by the electrodes turning green, all the ions in suspension want to travel to the oppositely charged electrode. Very interesting thing happens when they reach the cell, though. As the oppositely charged ions are attracted to each other across the cell membrane, but they can't move across it because of the presence of the cell membrane. So they position cells around the cell, forming an electric bilayer. This structure in front of you, again, is just a capacitor. Let me see if I can. Yeah, so this structure in front of you is just a capacitor. The more we have, or the more live cells we have, the more capacitance you have in your suspension. It is important to note here that we are measuring the buildup of charge around the live cell membranes. Therefore, capacitance is not only a reflection of cell density, but also cell size. We are effectively measuring the viable biovolume. And this is important to remember going forward, since it will be utilized we will be utilizing this very principle to our benefit in various applications that we discuss. In contrast, dead cells have leaky membranes with respect to charge, and therefore do not have the ability or the potential to hold charge around themselves as live cells do. Therefore, they do not contribute to the capacitance signal of the suspension. So for all intents and purposes, the Aber technology is insensitive to the presence of dead cells. Likewise, solid media particles, trub, air bubbles, for the same reason, do not have the ability to hold charge around themselves and hence cannot contribute to the capacitance signal. So how is this actually measured? The Aber probe simultaneously creates and monitors the electric field. Each probe has 4 electrodes made of platinum. The outer 2 electrodes create the electric field while the inner electrodes perform the measurements. More importantly here, the electric field that's generated is an alternating electric field on the radio frequency spectrum, typically around 50 to 20 megahertz, 50 kilohertz to 20 megahertz. So just to recap on some key points, live cells with intact membranes can be polarized in the presence of electric field generated by the Aber probe and then measured. Dead cells with leaky membranes with respect to charge, as well as solid media particles and air bubbles, are not measured. And then finally is quite an important concept, which is the resulting capacitance, which is the buildup of charge around live cell membranes, is actually a measure of total membrane-bound volume of the cells. That is to say, the capacitance is not only a measure of number of live cells present, but also the size of the cells present in the suspension. And I'll go into a little more detail, especially in viral processes, where that's a lot more important. So we have addressed 3 of the questions so far: who, why, and how. The final question is where. Where can the capacitance technology be used? So due to our wide range of offering, capacitance technology has been implemented in smaller scale bioprocess developments, such as shake flask, mini bios, which are shown on the left, and even single use shown in the bottom left. It's also been used in smaller glass bioreactors that are shown in the middle. We usually call them benchtop. And then even the large manufacturing vessels that range from 10 to 50,000 liters within manufacturing. So it's been used in all of those with great effect. In terms of the cells, the technology has had success in mammalian cells. So for example, CHO cells, HEK, NSO. We have also worked with insect cells, specifically the SF9, and I'll present some interesting data sets with SF9 and with HEK cells in just a little bit. The Aber technology works with yeast too. Both gram-positive and gram-negative bacteria can be used with dielectric spectroscopy. Fungal applications are also great candidates because they typically make for very difficult offline measurements. We've also had success with gene and cell therapy and also 3D tissues. The basic idea is if you have a dense enough homogeneous mixture of live cells with intact membranes, capacitance can be used to measure it. Overall, in terms of applications, the most basic use of Aber technology is to monitor your cell concentration in real time. Aber should provide a consistent graph of what your growth rate looks like for the same exact run every time. We call this your fingerprint. This fingerprint can and has been used for troubleshooting purposes. So whenever your culture deviates from that golden fingerprint, you know to troubleshoot for that. From there, our customers have been able to use this data to create automation for feeding and perfusion strategies. We'll see later on in this presentation how capacitance works for microcarrier applications. It has also been used to determine success of a scale-up process since it can be used as a key performance indicator across different scales. And we'll take a look at these later. Now, here is what an actual capacitance trend looks like. What we have here is a fed batch culture, which fed batch cultures are some of the most basic of runs performed in a bioreactor. The idea is to grow cells to a high concentration while the product is being produced. These were NSO cells that was fed at regular intervals with media. The blue lines represent the raw capacitance and the capacitance calibrated to read in cells per milliliter. The pink squares are the offline counts performed using CDEX. The two blue lines are the exact same trend, only the absolute values are different. It's just that the blue line, the light blue line, has a simple calibration factor applied that converts capacitance to cells per milliliter to match the offline counts. We can clearly see that as the cells grow, the capacitance increase, and as the nutrients are being depleted or consumed, the capacitance starts plateauing. More nutrients are then added, which causes the capacitance to dip due to the dilution effect. The cells then start growing again, and this is repeated. The advantage of using real-time technology can be seen as it provides a much more detail about what is going on with the process during the culture. However, there's an interesting point to be made here. Notice in some cases, the capacitance has started decreasing which means the cells have started dying before the nutrient is added. Now, it could be argued that these nutrients could have been fed much sooner based on the real-time information obtained from Aber Instruments. And this would allow for a prolong of the culture. In contrast, if you look at the offline samples, it does not provide enough detail in comparison to Aber, and lack of knowledge in the offline measurement is very apparent. The next example comes from a recent publication we had from one of our larger customers, Biogen. But before we take a look at that, of what was done, it's important to understand the background of this work. For any traditional manufacturing process, the feed amount is typically fixed. And this is based on historical batch data where a specific amount of feed is added at specific time points. This fixed feed strategy does not allow for any variation in cell growth or nutrient requirements in real time, which can lead to either over or underfeeding your process. And this over and underfeeding can directly impact titer and in general impacts the overall process performance of cell culture. Now, Biogen overcame this problem by utilizing a strategy based on the real-time raw capacitance value from Aber. Of course, there was a lot of background work before they got to this stage, but their strategy is now currently based on raw capacitance, which means they don't even try to convert capacitance to an offline method. And it's worth noting that this method is becoming increasingly popular with other companies adopting the same strategy. Now, for them, the biocapacitance controlled feed automatically adjusts the amount of feed in real time. And to prove this, they tested 3 strategies. In the first of they basically tested 3 different runs, run slightly different ways. The first was a fixed feed volume strategy that was known as their golden batch. So basically they fed the right number of cells, they did their perfect feeding that they normally do, and it was basically their control. The next was again with the same feeding strategy, but this time they intentionally put too few cells at the start of the run. And then on the third, it was the Aber controlled feeding strategy with the same number of cells, so the underseeding as seen in the second bioreactor. And the performance of these 3 cultures were assessed by comparing parameters such as viable cell density, viability, impurities, and finally product titer. So now, looking at the results from Biogen, we can see these 4 graphs. The first one is viable cell density and viability against time for the 3 strategies that I've just described. The second and third graphs represent undesired impurities, namely ammonium and lactate in the culture. And the last graph is the product titer for these 3 strategies. As expected, the culture that was underseeded but controlled using a fixed feeding strategy was inflexible and did not perform well. This culture was truncated by a few days since it started losing viability much sooner. And this was probably because there is an increase in concentration of ammonia and lactate caused by overfeeding the culture. The product titer, as you can see in the last graph, was also well below expectation. Interestingly, however, the capacitance-based automated strategy, even when used to control an underseeded culture, performed comparably to the golden batch. And this is because the strategy automatically adjusted for the nutrient feed in real time based on the nutrient demand of the cells going on. So basically what that came down to is, you know more about your process due to the real time, you can adjust better for it. So now we'll take a look at microcarrier applications. This, I won't spend too much on this slide, but this is from a publication which compared capacitance to more traditional methods of measurement. Namely, this is optical density and dry cell weight being compared to capacitance. In both cases, you can see an excellent correlation with an R² value near 1 between capacitance and dry cell weight, and then capacitance and optical density respectively, left to right, at high cell densities. This is interesting for us because most industries, they do want to compare with the offline measurement, because if you do research and development with dry cell weight or optical density, then a lot of times when you go into manufacturing, you want to use those same. So it's always important for us to say you can compare them, even though they may be measuring different, even though they are fundamentally different measurements. Here's just a quick example in extracts from 2 different publications, which demonstrate that capacitance technology has been used successfully in both gram-positive and gram-negative bacterial applications. And there are numerous other publications that we have that I can certainly share with anyone upon request. So now we'll move to another case study here. Here, much like Biogen, Dow, now known as Corteva Agriscience, decide to trust and use raw capacitance in their processes. An increasing number of customers are, again, trying to adopt these strategies for obvious reasons, such as you don't have compared offline measurement and it is real time. With Corteva, though, it was interesting because they were unable to develop a reliable offline measurement. So when they heard about capacitance and wanted to start implementing it, they had nothing to compare it to. They attempted optical density, dry cell weight, but because of basically the messiness of their media, they're unable to get reliable offline counts. But yeah, basically anything they tried just didn't work, so they tried capacitance instead. And so this graph shows the immediate effect of implementing capacitance for troubleshooting. For instance, in this example, they discovered that the day 3 product titer for tank P was much lower than that in tank E. When they consulted their capacitance trends, they discovered that tank P also had a much different trend line, which showed that it was indeed the number of cells causing the low production and not any other factors. This led them to develop process changes to get tank P more in line with tank E. Another application at Corteva where Aber capacitance was used was to determine feed timing, much like in Biogen. You can see on the graph here that before capacitance was used to optimize the process, the original feed was performed later, whereas the capacitance, it was optimized to perform much earlier. And this caused an immediate improvement not only on the cell growth profile, but it also improved their titer by 15% just by implementing a different feed timing. This is because the original later feed timing was during a period of cell growth, so they're feeding dying cells. Implementing an earlier feeding time based on capacitance allowed them to feed healthier reproducing cells, which led to higher cell density and higher product titer. So we've seen an example of the Aber technology being used to automatically control feed of complex nutrients in the Biogen case, whereas here are a few examples of controlling the actual cell concentration automatically using the Aber technology in real time. Perfusion is an interesting topic to talk about, as it is a very complicated process by design. The basic idea of perfusion is to maintain optimal cell density. This is very hard to do in normal circumstances, as it is difficult to track minor changes in cell density along the process. This is why capacitance technology is ideal, so that you can change your feeding and bleeding or cell removing strategies automatically based on the capacitance trend. The aim of this graph was to maintain the cell concentration, which is represented by the blue line and measured by Aber at approximately 25 million cells per milliliter. And this was done by connecting the Aber signal to a feedback control loop, which controlled the culture volume based on the Aber measurement. As the cell concentration went above 25 cells per milliliter, part of the culture was removed from the vessel, whereas when it went Below, more culture was added. And using a strategy, the concentration was maintained at the desired value for a longer period of time. So now let's take a look at some viral vector processes, as this seems to be the topic on everyone's mind at the moment. For a little background, viral vector processes are vital for creating genetic material used in many therapies, such as vaccines. The process involves using a host cell that becomes infected by a virus to heavily produce the material. Is an interesting application, as cells tend to slow down reproducing drastically after infection. But what they do is they swell up in size as more product is made. This is captured by capacitance, as it is more accurately measured of biovolume, which is cell density multiplied by the average cell volume. So let's explore the use of capacitance in such processes. This is the typical real-time fingerprint that you will see. So we have capacitance, aka biovolume, on the y-axis and time on the x. To begin with, capacitance monitors the growth of your host cells. So as the cells grow and multiply, your capacitance increases. Next, based on the host's growth profile, you can identify and optimize and also possibly automate the infection or transfection point. This is found based on past research that has determined the optimal infecting concentration. Once infected, typically capacitance tends to increase sharply. This is thought to be due to the increase in cell size following viral DNA replication and the differing electrical properties of the cell membrane upon infection. This increase in measurement allows capacitance to be used as a key performance indicator for successful infection. The capacitance profile will also provide an indication of peak infection point, which coincides with the maximum capacitance observed in the culture. The identification of peak infection point is said to be very important since it is directly linked to time of harvest or the time with the highest product titer. Following the peak infection, as the cells begin to die to release the product, capacitance decreases sharply. As we learned early in presentation, dead cells or lyse cells do not hold the ability to hold charge, and hence the capacitance technology will not detect these. This is why you see such a sharp reduction in capacitance as the cells lyse and the product is released. Finally, based on the real-time profile, capacitance can help you identify and optimize again the harvest point. This is quite important event to optimize and identify since it's closely linked to titer, quality, and consistency. This graph is a lot busier, but shows real-life data of capacitance technology being used to monitor viral product production. As we discussed in the previous slides, the Aber measurement is a measure of the live biovolume of the culture. This real-time cell change information to benefit a deeper understanding of your process. Take this example in front of you. This is where the Aber technology was used to detect SF9 insect cells that were being infected with a virus. The continuous black trend is the capacitance. Then the trend in the circles is offline cell density, while the ones in diamond are cell size. You see up until the infection point where the cells were infected with the virus, capacitance and offline density match very well. While after infection, you clearly see that the offline cell density plateaus, whereas capacitance kept increasing sharply. And this is exactly the time you may have noticed cell size begins to increase as well. So this was clearly a case where capacitance was responding to the cell size changes, and this was quite valuable information for the process because the capacitance profile and its increase post-infection was used as parameter to determine successful infection. And of course, because of the detail in the complete capacitance profile, you can also determine peak viral infection and when the cells start lysing upon release of the protein. So essentially, capacitance represents the live biovolume, which allows for a full understanding of this process. All right, so as I mentioned earlier, when it comes to biotech developmental processes, an effective scale-up strategy is important. This is very important in industry because typically when you're researching a new process, you begin in much smaller bioreactors that typically can fit on a benchtop. But once you develop a great process that fits a pharmaceutical need in the world, then you want to be able to develop it into larger bioreactors capable of producing high quantities of product. The trick is to find scalability indicators. So, if it looks this way on the benchtop, it should look this way in the larger bioreactors. Capacitance has been proven to be a good scalability indicator. Here we have an example where Biogen assessed the scalability of capacitance sensors from benchtop to their manufacturing scale, so from 5 liters to 15,000 liters during the exponential phase of growth. As you can see, there's an excellent correlation that was seen across all scales between capacitance and offline viable cell density with an R² value close to 1. This tells them that if you are able to achieve similar capacitance trend across all bioreactor types, then you can confirm proper scale up of your process. The next application that I'd like to discuss is using Aber technology with microcarriers. So this is quite an interesting example of measuring baby hamster kidney cells attached to macroporous microcarriers. Microcarriers, much like dead cells, gas bubbles, and solid media particles, do not have the ability to hold charge around themselves and are, as a result, not detected or measured by the Aber technology. The green line here is the capacitance trend calibrated to read in cells per milliliter. As the cells on the microcarriers grow, the capacitance increases. And as the nutrients are depleted, the capacitance starts to drop. Interestingly, the agitation was stopped at regular intervals such that all microcarriers along with the cells dropped to the bottom of the vessel, and this meant they were no longer in the measurement field of the Aber probe, which caused the capacitance to drop immediately. Once the carriers were at the bottom, all of the spent media was flushed out and fresh media was pumped in. The agitation was started again, the cells come back into the measurement field and the growing in the fresh media, which is again reflected by the capacitance signal. The detail in this capacitance measurement is extremely useful. In contrast, the offline counts, which are represented by the red circles, as expected, are highly variable. This is expected because of the challenges of offline sampling and measuring immobilized cells on microcarriers. So this concludes the application section of the presentation. I hope this gave you a glimpse of the capabilities of the Aber systems, and know there's a lot more resources of applications that Aber has been used for. But we'll move on to the highlights and the take-home messages of the presentation. We discussed how Aber capacitance measurements provide real-time estimates of total live biovolume of your process and the value that this brings. The ease of use and plug and play of this technology allows for it to be used in many different types of bioreactors. And it also comes with the inherent benefits of reducing or replacing the need for laborious and risky offline measurements, and has been successful in a lot of applications that don't have any other option. Then, moving on to the scalability of the systems, for which we can provide publications of empirical evidence showing that the scalability is there through research. We also discussed how the Aber technology can be used for various applications, including but not limited to the ones discussed in this presentation, and it's been used to both monitor and set up automatic control regimens for troubleshooting and much more. Aber has a vast experience in installations from R&D and process development to good manufacturing process productions environments across esteemed sites all around the world. And finally, it can be used as a critical process analytic tool to provide better understanding and control of bioprocesses. Thank you for listening. That's the end of the presentation. I'll take any questions.